So why don't our soup cans look like boxes? We would draw this soup can. It would be 7.398 centimeters across. Bless you. And it would be 7.398 centimeters tall. It's as wide as it is tall. Does our soup can look like that?
No.
No, our typical soup cans don't look like that. In fact, our typical soup cans look like about 1.5 times as tall as they are wide. That's what this point says right here. They're 1.5 times as high as they are wide. Okay? So if this curve, and that curve should look familiar from yesterday, ladies and gentlemen, if that curve represents the surface area of the metal we use, and we minimize the surface area, are we making our ideal can? Are we using minimal material?
No.
No. Why not?
Because one's lower.
Yeah, I agree, because our soup can's over here, and here is our results from our calculations. We have this 1-to-1 ratio of overall width to height. But why don't we design things to minimize our material in a day and an age where we like to recycle or conserve?
Might not be practical.
Might not be practical. Any ideas as to why Campbell's company might not want to change the design of their soup can? Okay, so Ryan says it's already a really popular thing. People know what to look for when they are looking at the shelves. Look at our tuna cans, right? Our tuna cans are definitely squatty. Are they optimizing their material use either? Nope. What about our soda can manufacturers? Are they optimizing their material use? Nope. Barely anybody does. A lot of it is brand recognition.
They can get more money.
They can get,
Like if there's less in the.
if there's less in the can, price per ounce, they can increase their profit.
Hold it comfortably.
Okay, yeah. How would you like to try to hold something that is 7.5 centimeters wide? It's not easy to hold, is it? Okay, so there's that factor too. So there's a whole bunch of reasons why they don't optimize their material use. Okay, we're going to still look at construction type problems. Okay, we're going to still look at maximizing or minimizing volume or surface area or something. So what I want you to do in your groups is I want you to crank out these 2 multiple choice questions. I'll give you a hint on 29. Absolutely no calculus involved whatsoever. It's a trig function, folks. Let's talk about maxes and mins of sines and cosines. Do you know them without doing any calculus? Maximum value of sines, maximum values of cosines. Becca's saying maximums are ones, awesome. Minimums are
-1.
super. No calculus involved. So crank those out, report your answers to me. Okay, and then once you're done cranking these out, you're off and running on websites. We have definite consensus that is C. Okay, so that's pretty cool. We've got absolute value of 1 minus a half and an absolute value of -1 minus a half. And this is definitely what maximizes f of x, or f as they call it. So awesome job there. I agree.
Miss Potter, I have a question.
Okay, so if we look at this, the aluminum can question, just out of yesterday's notes, literally, okay, we've got a volume of 16 pi, and the volume is pi r squared h. So we need to solve, and they like to do this. They like to do this on multiple choice questions, give you a volume in terms of pi, so the pi's cancel. So the math is easier, so you don't need a calculator. Okay? So we're going to solve for h here, which means we're going to divide by both sides by what?
Pi r squared.
By pi r squared. Okay, notice the pi's cancel. That's by design so that you don't need a calculator. And h is 16 over r squared. And then we have to know our surface area equation. So we have a tin can. Top and bottom are what sort of shapes?
Circles.
Pi r squared. How many are there?
2.
2 of them. And then we need the side, the curved surface of the can, which has a height of h and a width of 2 pi r. It's wrapped around the top and the bottom, right? And the distance around the top and the bottom of the perimeter. So now we can plug our h into there. We got a 2 pi r squared plus 2 pi r times 16 over r squared. Okay? So we've got a 2 pi r squared plus 232 pi over r. You know what, though? I'm going to write that in a way that's easy to take the derivative. So I'm going to write that as r to the negative first. There's our surface area. What do we need to do with that?
Solve for
Can you scroll it up?
Yep. Now, before we solve for r, what do we need to do? Yeah, we haven't optimized anything yet until we take a derivative. Because optimizing means we're going to look for a critical point. So we have to take the derivative of that. Then we can set it equal to 0. Okay? I know half of you are kind of about there, so why don't you go ahead and take that derivative and set it equal to 0. Notice when you set it equal to zeros, there's only one. When you set it equal to 0, your pi's are going to cancel when you bring one thing to the other side. That's the beauty of expressing volumes and areas in terms of pi on circular efforts. So as I see people crunching along here, I'm seeing a lot of 4 pi r equals 32 pi r to the minus 2. And we can put that and make that a positive exponent by putting it back in the denominator. And then we can do our cross multiply. Notice this is the whole design of a multiple choice problem like that. Our pi's cancel. That was all created because we had a volume in terms of pi. So that they like that pretty stuff on multiple choice questions because they know that you don't have a calculator. Okay. And then we get the answer after we crank it out. We get an answer of. Anybody want to tell me what we get for r? Good. We get an answer of 2 for r, which is not the answer for the question because the question is asking for the height. Exactly. So what happens when we plug 2 back into here?
2 squared is 4.
Yep.
Is equal to 8.
Yep. So the height is equal to. When we optimize, how wide is this can? Careful. Our width of our can is 4. What's the height of our can? 4. If that can were square, we would call it a what? A cube. When we optimize things, we start to make cubes and squares. Okay? Always. Okay? So think, kind of keep that in the back of your mind to make things a little quicker. Okay? My rules on the multiple choice will be find the derivative for me and solve it because I would want to see that process. But rules on the AP exam are come up with the answer. Okay? So it's important to realize that when we optimize things, we start to square things out. We start to make squares, we start to make cubes. all that sort of stuff, okay?